This is the second video on kinetic energy and work. Let's assume we have some object on the ground and we are going to apply a force F with an angle theta. And because of this force, this object is going to move a certain distance. Let's call it d. So if we look at the x component and use F equals ma, and also just assume there's no friction. So what we have is F cosine theta is equal to max. So from kinematics, if you remember our trusty equation, v squared equals v0 squared plus 2a delta x. So in this case, I'm going to write 2a x d because we are looking at just the x-axis. So what we have is 2a x d is equal to v0 squared actually let's go back here. What I have is v squared minus v0 squared. So if I just isolate ax, what we have is 1 over 2d times v squared minus v0 squared. Okay, so now what I'm going to do is plug this ax back here. So what do we have? We have f cosine theta is equal to m times 1 over 2d times v squared minus v0 squared. And I'm going to take m inside the brackets as well as the 1/2. So if I isolate just 1 over d, what do I have? We have 1/2 mv squared minus 1/2 m v0 squared. So if I multiply both sides by d, what do we get? We get f d cosine theta equals 1/2 mv squared minus 1/2 m v0 squared. So if you remember from the earlier video, 1/2 mv squared is kinetic energy. So because this v is the final velocity, we can say this is the final k, final kinetic energy, and then this is the initial kinetic energy. And here where we have ft cosine theta, we define as work. So what we have is work, and we use W for work as well as weight, so be careful, equals kF, which is the final kinetic energy minus the initial kinetic energy. And we call this the work kinetic energy theorem.